Hello, this is Dr. Mears, and today we're going to learn about radical graphs and expressions. What's a radical expression? It's a number or expression under a radical symbol. So square root of 3, square root of x plus 3, those are expressions. We're going to be looking at square roots. An equation, a radical equation, is f of x equals the square root of x, where we have an expression, but then it's set equal to f of x. And this is the graph. We have x, this is f of x, and this is the graph of this radical equation. What we're going to do is, as you can see, there is a restriction on the domain. So for our x values here, we see that it starts at 0 and then goes all the way, all the positive numbers. So this does keep going. And what we're going to have to tell a person reading this graph is that we're not going to have any negative x values over here. So our restriction on the domain is that x is going to be greater than or equal to 0. And that's what we see here. Here at 0, here it would be at 2, 4, 6, 8, and it keeps going to all the positives. So we're not going to have a negative number underneath the square root. Why do you say? Because we cannot take the square root of a negative 4. This is actually an imaginary number. We are going to be getting into imaginary numbers, and so you will see us take the square root of negative 4, but because it's imaginary, it's not on this graph right here. So we are going to have to restrict the domain. We cannot have negatives underneath the square root. No negative numbers under square root. And so that is our restriction. No negative numbers underneath square root. Okay, let's look at another graph and do the same thing. So here we have f of x equals x minus the square root of x minus 8. And here we see the graph. And I'm just going to make this bigger. This is 8. I can't really see it. I should have made the picture a little bit bigger. I tried to get it on one page. So as we can see, here's x, here's f of x. This graph, this curve, starts at 8, and then it continues going 10, 12, all the way to all the positives. And you'll notice there's no curve over here. That's because there's a restriction on the domain. The restriction is this underneath the square root, x minus 8 we cannot put any number that would make it negative here. So x minus 8 has to be greater than or equal to 0. Because if it's not greater than or equal to 0, we're going to have a negative number under the square root. So let's say if we put in 7. So 7 minus 8, let's say we did that one. Let's say that x equals 7. We put 7 in, 7 minus 8, we get the square root of negative 1. We can't have that because that's an imaginary number. So that's why we have to make it greater than or equal to 0. Just like we were doing for rationals where we set it not equal to 0, this needs to be greater than or equal to 0. Remember, no negatives. So now let's just go through and solve. Plus 8, so x is greater than or equal to 8. So we cannot have any numbers less than 8. Because we saw here, if we put in a number which is less than 8, so if we put in 7, we get imaginary and we can't have that. So that's how you find the restriction on the domain. Let's look at just one more. And this is going to be f of x equals the square root of 8 minus x. And if you notice, it just flipped over. So this is at 8. It starts at 8. Here we have x, f of x. And as you can see, this is going towards the negative numbers for x, negative 2, negative 4, negative 6, negative 8. And so our restriction on the domain is going to be all the numbers that are bigger than 8. And so let's say that we put x equals 10. Let's say that we put that in here. So we have the square root of 8 minus 10. So we have the square root of negative 2, and we can't have that. So any number that you put in over here is going to get us, we can't have it because it's an imaginary number. So restrict the domain. We're going to take what's underneath the square root, x, 8 minus x, has to be greater than or equal to 0. I always stick with the greater than or equals to first. I know what you're thinking, like, wait a minute, but, so it's okay. Stick greater than or equal to 0. This is the part that you always write down. Underneath the square root, and then greater than or equal to 0. Let's solve it. Minus 8 minus 8. Negative x is greater than or equal to negative 8. Now be careful because this is a negative 1. And when we divide by or multiply by a negative number, this symbol switches. So instead of greater than, it's x less than or equal to negative 8 divided by negative 1 is positive 8. So x has to be less than or equal to 8. And that's what we can see here. 6 is less than 8, checks out. 4 is less than 8, 2 is less than 8. So just be careful when you're dividing by a negative number. That inequality is going to flip, and it is going to stay true to that graph. So that is the restriction. X has to be less than or equal to 8, because if it's not, if it's greater than, we get an imaginary number. So always take what's underneath the square root, set it equal to greater than or equal to 0, and then it will work itself out to get to the right place where you're going to find the numbers. We're restricted that we can only use numbers less than 8. Okay, now we're going to be simplifying square roots. So we took care of graphs, let's simplify. I have a little table here for you. This is really handy if you want to take a picture. You can even take a picture with your phone. It's all of the perfect squares. So square root of 1 is 1, square root of 4 is 2, square root of 9 is 3. Perfect squares, meaning we're not going to come out with any decimals. And I went all the way to 20. So this is helpful when we start to simplify. And I'm actually going to get a piece of paper here because, all right. So we're going to break some down. So here we have the square root of 20 and the square root of 45. Let's take care of the square root of 20 first. If you notice on this sheet, if we look square root of 20, we don't have the square root of 20 here. So the square root of 20 is not a perfect square. If we had the square root of 25, you would just say it was 5. Because what a square root symbol does, this square root, this means, let's say 25. What number times itself gives you 25? That's what this symbol means. And we're going to say, oh, 5 times 5 gives you 25. So the number that gives you 25 when you multiply it by itself is 5. You don't see 20 here because it's not a perfect square. So what we're going to have to do is, and I'm just going to show you the whole paper. What we're going to have to do is we're going to have to find that perfect square that we can divide 20 by, and then find that other factor. So 4 times 5 gives you 20. 4 is that perfect square. 5 is the factor. So 20 divided by 4 is 5. And what we can do now is we simplify the perfect square. The square root of 4 is 2, so I simplified. And then you just bring down the square root of 5. So this is a simpler version because 20 underneath the square root is bigger than 5 underneath the square root. So when you simplify, when you break them down, you want the number underneath the square root to be as small as possible. Number under square root, or we could say radical symbol, the radical, to be as small as possible. A little side note in our cloud here. Okay, 45. Now 45, again, is not a perfect square, so let's bring our perfect squares back out. Okay, so we have square root of 25, 36, 49. We do not have the square root of 45. But what perfect square can we divide 45 by? And hopefully we see, wait, we can divide 45 by 9. And 9 is a perfect square. And so that's what I did. Here's my perfect square, 9 times 5 gives me back 45. So these two have to multiply. That's why I have that little dot there, multiplication. These have to multiply to get you back. So here we have our perfect square. Here we have our factor. Since we can take the square root of 9, I do. Notice there's no more square root symbol over it. and then times the square root of 5. I cannot take the square root of 5, so you bring it down. This does mean multiplication here, so I just don't put the little dot symbol. You don't need to. If you just attach it, it's kind of like saying 3x, 3 times the square root of 5. So here is your answer. Simplify, the number underneath the square root is as small as possible. Okay, the square root of 50. Again, 50 is not a perfect square, but we can divide 25 by 50, and 25 is a perfect square. Now we need the factor, so 25 times 2 gets me back to 50. Take the square root of 25, that's 5, and then square root of 2 just comes down, okay? Don't take this out. You can't take the square root of 2. It is not 1, because 1 times 1 is 1. So be careful. It's a very common mistake. Okay. 18, again, 18 is not a perfect square. If we look back at a perfect square, we see that 16 is a perfect square, but not 18. What can we divide 18 by? That's a perfect square. I'm thinking 9. So we have 9 times 2. We have 9 is a perfect square, so it comes out of the square root. 3 times 3 is 9, so that's 3. Bring down the square root symbol and bring down 2. Simplified it because this is the smallest number possible. So your game that you're playing is you're trying to get the largest perfect square that we can divide this by. That's your game because that's going to get this to be the smallest number. Okay. Next, let's involve some variables. I have a little side note over here. Our side note, it says x to the exponent divided by root. And this is going to help us out. So exponent divided by root. And that's a little up in the exponent position. So here we have square root of x squared. Now, there is a little 2 that hides in that corner, but it disappears. We don't write it because when we say the square root symbol and there's no little 2 there, it just disappears. So if there's no number here, it's really an imaginary 2. I want to put my little imaginary 2s, not imaginary number, just it likes to disappear. Okay, and so what we have here is we have the exponent and we have the root. And in order to simplify this, we can undo the radical symbol by saying exponent 2 divided by root 2. And 2 divided by 2, yes, is x to the first power. And you can just simply write x as your answer, and that's it. This is going to definitely come in handy along the way. All right, number 6. We have the square root, so we have a little 2, square root x cubed. Now, if we did x to the 3 over 2, exponent 3 divided by 2 root, it would just, we would still need to simplify. So how we simplify this is just like what we did up here. I'm going to break it down. All right. Within x cubed, we have an x squared times x to the first. Another side note, when we multiply variables with the same base, we add their exponents. So you really want a factor of whatever root that you're taking, because we know here's 2. X squared, the square root of that is x. So we just did that one over here. So I'm going to write x down. That's just this. And then we cannot take the square root of x to the first, so we just bring it down, just like we did here. So if you can't go any further, we just bring it down, and this is our answer. All right, let's try another one. We have x square root of x to the 4th. All right, so let's put it in fraction form and see. So we have x, exponent is 4, root is 2. Oh, look, we can divide that. X, 4 divided by 2 is 2, and so that's our answer. It's x squared. Great. So if it's a factor, if the exponent is a factor of a root, that's what we're looking for. Exponent or root is a factor of the exponent. There we go. They have to work out. Root is a factor of exponent. Because 2 times 2 is 4, so it can divide. And so that's what we're looking for here. We have the square root of x to the 5th. Okay. We can split up x to the 5th. And you got it. This is going to be 4 and 1. So here we have 4. The root is a factor, 2. Remember, that's 2. So this would be x to the 4 over 2. We cannot factor x to the first, so we bring it down, square root of x. We can simplify, so this is x squared times the square root of x. So we're really looking for these to be able to be divided. The exponent has to be divided by the root. So if you want to think about it like that, exponent can be divided by root. And that's what we see right here. So that's what you're looking for. All right, let's keep going. All right, let's look at simplifying other roots. So this is a cubed here, and it looks a little blurry, so let me write it out. This is the cubed root of 27. That's what we're, nice, much bigger. And so what this is really saying is, what number 3 times itself gives you 27? What number 3 times itself gives you 27? Okay, we can do this a couple different ways. So we could, this is to the first power, in the calculator, we could do 27 to the 1/3 power. And when you do that, exponent divided by root, when you do that, you're going to see that it's 3, because 27 is a perfect cube. Or you can think about it like this. We have, here's cube, 3 to the 3rd power, 3 times 3 times 3. And so since this is a perfect cube, 3 over 3 is 3 to the 1st, which is 3. So we're really introducing different ways to think about roots. Okay, number 9. 24 cubed root of 24. So in the calculator, you could put 24 to the 1/3 power, because that's a 1. So this was 3/24. So that's a power of 1. So I'm just rewriting it for you so that it's a little bit bigger. When we do that, let's just look. 24 to the 1 divided by 3. Let's see, can you see it? Okay, let me go like this. Okay, let's see what happens. We get a decimal, we get 2.884, which means it's not a perfect cubed. If I put 27 in there, you see that we get 3. I'm probably making you dizzy by trying to get the calculator. There we go. So it's not a perfect cube. So we have to think about, can I break this up? So not a perfect cube, so we can't go this way. So I'm going to stop. Can I break this up? Can I break this up so that we have a perfect cubed here times the factor? So right here, perfect cube. So is there a perfect cube? Yes, there definitely is a perfect cube, because we can see that 2 times 2 times 2, or 2 to the 3rd power, that gives us 8 times 3. So this is 3. So 8 times 3 is 24. 8 is a perfect cube. And it's not going to be grabbing onto this concept. It takes a lot of practice to realize that we're talking in perfect cubes. And you can use the calculator. You might need to do 2 cubed is 2 times 2 times 2. So you might need to even write these out. 3 cubed is 3 times 3 times 3. So this is 8 and this is 27. So if you want a little page where you have your perfect cubes, you can. We're not going to go too deep into this. If you know your 2s, 3s, and 4s, that would probably be good. Okay, so 2 cubed to the 3rd is just 2. Good, because 3 divided by 3 is 1. And then we're going to bring down 3. And notice I keep writing this 3 here because that was the original. So the answer is 2 times the cubed root of 3. So we're doing the same process, It's just you really have to look to see, are you dealing with cubes? Are you dealing with squares? And so let's go on and do a few more. Okay, number 10, we have the cube root of x cubed. And so I like to write on my side of paper, I like to write x to the exponent over root. And I just write it like that, e over r, xer. Okay, so here we have exponent, here we have root, so it's going to be x to the 3 over 3, which is x. All right, now we have the cubed root of x to the 5th. So again, we can split these up. And so we need to be able to divide this exponent by this root. I'll put a little 3 here. And so that's why I divided these up to x cubed times x squared, because 3, and remember, when we multiply these, we add their exponents. Okay, that's how I can divide them out. So the cube root of x cubed is x. We just did that here. And I cannot go any further, so I'm just going to bring down this x squared and put it under the cube root symbol. All right, 64. I'm going to think about this the same way. Number 12. So the 5th root of 64. So this was a 5. I'm going to write it a little bit bigger, 64. When I see these, the game that I play is, this is probably divisible by 2. So in the calculator, I see what I can do. What is 2 to the 5th? What is 2 to the, if I multiply it? And so it really is a game of practicing your 5th roots, being able to multiply, because this 5 says what number 5 times itself. And I'll put a little 5 in there. Okay. And if you can see a pattern, you can try out 2 to the 5th and see if that can get you a factor of 64. It's really all about factoring. You probably remember factor trees. Okay, so 2 to the 5th divided by 5. We cannot go any further, so I'm just going to bring down the 2 to the 1st. And so 5 divided by 5 is 1, so this is 2 times the 5th root of 2. Okay, next. The 4th root of x to the 4th. Okay, hopefully you're getting the hang of this. 4 divided by 4, which is x. All right. And our last two for today, number 14 and 15. Number 14, we have the cubed root of 216, x to the 5th, y to the 6th. We're going to take this step by step. As you can see, I have 3 different ones. First, 216. And 216 is a perfect cube. If you try it out in your calculator, just keep multiplying numbers, and I'm going to put it down here, 6 times 6. 6 cubed, which equals 216. So you might want to try out in the calculator to see. You could have put in your calculator 216 to the 1/3 power, and it's going to give you 6. So either way you do it, I would try it out, and just to make sure, so that you're not worrying about it. So I think this is the easiest way in the calculator, because you might come out with a whole number. All right. Now, so I did 2 is 6. X to the 5th. So we have the cubed root. So let's break up x to the 5th, and you got it. It's going to be x to the 3rd times x squared. And we have y to the 6th. And hopefully you're saying, wait a minute, if we take the exponent over the root, we are going to get a nice number. We're going to get 3, because 6 divided by 2 is 3. So we don't have to break up y to the 6th, because we'll just be able to take it out. All right, now let's take out what we can. Can we take the cube root of 216? Yes, we saw it down here, so that's 6. Can we take the cubed root of x to the 3rd? Yes, x to the 3 over 3 is just x, so x. That's out, that's done. Can we take the cubed root of x squared? No. When this number is smaller than this, we can't do it. So I'm going to write it over here, x squared. And can we take the cubed root of y to the 6th? We can, so that's y to the 3rd. So this is all multiplication. You write your answer just like that. If you want to move them closer together, you can. Okay, and the last one, the 5th root of x to the 7th, y to the 18th. Let's take it step by step. Okay, so 5th root of x to the 7th. So let's break this up to x to the 5th times x squared. 5 plus 2 is 7. And hopefully you're seeing that what I'm really doing is I'm just subtracting it. So 7 minus 5 is 2. So 5, let's do a 7. So I want to make sure that I can do 5 divided by 5 here. That's really what I'm doing. And y to the 18. So I'm going to actually break this one up to y to the 15 times y to the third. 15 plus 3 is 18. Now, why did I select 15 and not 5? Because 15 divided by 5 does give you 3. So I'm trying to simplify as best as possible. Okay, what comes out of the square root? X to the 5th divided by x to the cubed root of x to the 5th is x. That's done. I can't take this out. This is smaller. This exponent is smaller than the root. So I'm going to move it over here. 5x squared. Okay, that's out. Can I take the 5th root of 5? Yes, we just saw it here. Exponent over root. So it's going to be y to the 3rd. And can I take the cubed root, the 5th root of y to the 3rd? No, this number is smaller than that. So I'm going to write it underneath that 5th root symbol. And so this is how you simplify all of our exponents with the 5th root. This has been a deep, quick, well, kind of quick dive into radical expressions and equations. I hope it helped.